For the next block of study, we're going to get into total air conditioning. And so in order to do that, we have to first talk about psychrometrics. So let's start by doing basic definitions. Let's start with the definition of atmospheric air and how we model atmospheric air. So atmospheric air is a mixture of dry air and water vapor. Up until this point, we've just been considering air as dry air. So just the gases that comprise air, 78% nitrogen, 21% oxygen, 0.9% argon, and 0.03 carbon dioxide, and then miscellaneous other gases to make up the remainder. But in reality, you know that if you go outside on a hot summer day in Alabama, you can feel the humidity in the air, the moisture. So you know there's actually water vapor there. And that's when people say, oh, it's a dry heat versus it's a humid heat. Depending on your environment, how much moisture is in the air affects how you feel. So now we're going to start treating air as atmospheric air, so a mixture of dry air and water vapor. And that's kind of exemplified in this diagram, figure 11.1, this model of atmospheric air. It's just a simple device to show you that we have dry air. So all these gases, we're just going to talk about those as dry air, treated as an ideal gas for dry air. And then scattered amongst that, distributed equally amongst that, is water vapor, which we'll model also as an ideal gas. And this atmospheric air filling some volume has some temperature and some pressure. Now let's go back and remind you of some chemistry. Dalton's law of partial pressures. That's kind of key to the understanding of how we model atmospheric air. So Dalton's law of partial pressures states that the total pressure of the gas mixture, so of this atmospheric air, is equal to the sum of the partial pressures of the component gases. So the partial pressure of the dry air and the partial pressure of the water vapor. So if we write that in generic terms, that's equation 11.1. It's the total pressure is equal to the sum of the partial pressure of I number of individual gases. And let's be specific about what that partial pressure is. Partial pressure states that if some gas I, whatever gas it is, in this case, let's say it's water vapor. If water vapor, the only thing that exists within that volume, what pressure would that water vapor by itself exert on the system? And you do the same thing for dry air. If it was only dry air, what would be the pressure that just that dry air alone would impart on the system? And then, therefore, I can add them together to get what the total pressure is in this system of atmospheric air, and that's equation 11.2. Now, a key thing to note is that while the total pressure is the sum of the partial pressure of the air, the dry air, and the partial pressure of the water vapor for atmospheric air, the volume of the atmospheric air is equal to the volume of the dry air, which is also equal to the volume of the vapor. So each independently would still take up the entire space, so the volume's the same. Same thing with temperature. If I were to measure the system, the temperature of the atmospheric air is equal to the temperature, because it would be in equilibrium, the temperature of the dry air alone and the temperature of the water vapor alone. So using those concepts and relating that using the ideal gas law, the fact that we cannot model atmospheric air as an ideal gas, but treat the dry air as an ideal gas, and separately treat the water vapor as an ideal gas, and then relate those, we can come up with what's called the component mole fraction, X sub I. So that's the number of moles of some component I per total number of moles in the mixture. Let's put that in the equation. So in the book we go through this derivation, but we've simplified it down into the end result here. This is equation 11.6 and 11.7. And what that's telling me is that my partial pressure for air is equal to the ratio of the number of moles of dry air over the number of moles in the atmospheric air, so the number of moles of dry air plus the number of moles of water vapor times the total pressure. And so I can simplify that by just calling it X sub A, or the component mole fraction of the dry air, times the total pressure equals the partial pressure of the air. And the same thing is true with the partial pressure of the water vapor. The only difference now is, of course, it's the ratio of the number of moles of water vapor over the total number of moles in the system times the total pressure in the system, and I can shorthand write that as X sub V, where the component mole fraction of the water vapor times the total pressure equals the partial pressure of the water vapor. So now let's start defining some things that you're going to need to know in order to solve these problems, the first of which is humidity ratio. And it's important to get these terms down, and when we talk about the psychrometric chart, we'll learn how to look up all these values, and I'll show you some equations to compute them as well. So humidity ratio, lowercase omega, is the ratio of the water vapor vapor mass to the dry air mass in the atmospheric air. So what's the ratio of mass of water over mass of dry air in the system? And the units for this would be something like kilograms of water over kilograms dry air. And it's important to differentiate what fluid you're talking about, the dry air or the water. So these won't just cancel out. Your units would be kilograms of water over kilograms dry air. If we're talking about English, pounds mass of water per pound mass dry air, etc. You may see in some other usages and some other textbooks humidity ratio defined as called the specific humidity or the absolute humidity. All three of those terms are interchangeable. So if I write that mathematically, that the humidity ratio is the ratio of the mass of the water vapor over the mass of the dry air in the system, and then I solve for those respective masses using the ideal gas law, which is done in your book, we can come up with the following relationship that the humidity ratio is equal to the ratio of the masses, but it's also equal to 0.622 times the partial pressure of the vapor, over the partial pressure of the dry air. And those are equations 1110, 1111 respectively. And the interesting thing is this, that 0.622 number comes from relating the ideal gas law, and then it's the ratio of the vapor specific gas constant over the dry air specific gas constant. And so it doesn't matter whether you're working in metric units or English units, it'll always come out to 0.622, which is why you have that numeric value regardless of your unit system for your humidity ratio. Let's talk about relative humidity, and that's phi. Relative humidity is the ratio of the water mass, so that mass of the vapor in the air, compared to what the maximum amount of water vapor mass that atmospheric air can hold at that given temperature and pressure. And so when it's holding the maximum amount possible, that's what we call saturated, and that's in a percentage. Right? So 100% would be fully saturated. So we write that as the mass of the vapor to the mass of the maximum water vapor mass if it were saturated. And we can relate that using ideal gas law in simplifying terms to a ratio of the partial pressure of the vapor over the partial pressure of the saturated gas, or the saturation pressure. That's equation 11.13 in your textbook. So let's talk adiabatic saturation temperatures. So that's the temperature that atmospheric air would attain if it was cooled adiabatically to 100% relative humidity, to saturation, to when the water vapor, the mass of the vapor, is the maximum amount of vapor that atmospheric air can hold. And so this is seen in figure 11.3, an adiabatic saturator. So adiabatic meaning there's no heat transfer to the surroundings. I have atmospheric air with some temperature, some absolute humidity, and some relative humidity. And it's some relative humidity less than 100%. And as it comes in here, I've got makeup water, and we're just adding moisture to the air until it becomes fully saturated, or a relative humidity of 100%. And we had to add some water vapor in the system to do that. And so in order to do that, the relative humidity, the absolute humidity, or the humidity ratio, increased from state 1 to state 2, and the temperature as a result decreased. So wet bulb temperature. In the Army especially, you've seen this. You have to get your wet bulb temperature when you're out in the field. And what that is the lowest temperature that atmospheric air can achieve exclusively by evaporative cooling. And that's similar to the process in an adiabatic saturator. And you guys know when you use a wet bulb thermometer, one of the parts of the wet bulb thermometer is to get the little sock wet and then evaporate. And that thermometer will read that temperature due to evaporative cooling, and that's your wet bulb temperature. And you compare that to your dry bulb temperature, and that's how you get your heat category. Mixture enthalpy. Mixture enthalpy, like any enthalpy, is a convenience property, but mixture enthalpy is a specific convenience property for atmospheric air, which is that mixture of dry air and water vapor. So let's see how we derive that. So if we said, what's our mass flow rate times the enthalpy of the overall mixture, I'm sure you would agree that that's equal to the mass flow rate of the air times the specific enthalpy of the air plus the mass flow rate of the water vapor times the specific enthalpy of that water vapor. That's equation 1114. Now, if I factor out the mass flow rate of air, right, and that means I have to divide the mass flow rate of the vapor divided by the mass flow rate of the air, right? So if I factor this mass of the flow rate of the air through the parentheses, you'd see it would return to my original equation 1114. So to make it true, I have to divide this. You could see that the mass flow rate of the vapor over the mass flow rate of the air, that looks familiar. And what that is your humidity ratio. So let's replace that with humidity ratio. So I can say that my mass flow rate times the enthalpy of my overall mixture is equal to the mass flow rate of the dry air times the specific enthalpy of the dry air plus the humidity ratio times the specific enthalpy of the water vapor. Well, if I group this last part here, I can call that mixture enthalpy. So as shorthand, we call it mixture enthalpy. And when you look at a psychrometric chart, that's what you're going to look at, is your mixture enthalpy. That's the value you're going to get, and that's what it equals. And so I can simplify this equation now to say my mass flow rate times my enthalpy of the overall mixture is equal to the mass flow rate of air. That's a key caveat. The mass flow of the air times the mixture enthalpy. That's equation 1117, and that's an important one, an important relationship for you guys to remember. Okay, let's talk about mixture volume per mass of dry air. That's a convenience property for atmospheric air, and is the ratio of the volume of atmospheric air to the mass of dry air. So let's write that down below. So it's a ratio of my volume of my atmospheric air to the mass of my dry air. Well, remember what I said on the first slide. I said, hey, the volume of the dry air, the volume of the water vapor, and the volume of the atmospheric air, the total system, are all equal. So if I were to replace this volume with the volume of the dry air, you would agree that that is the specific volume of the dry air. So these things are equal. And I could also relate that using mass flow rate. So the volumetric flow rate divided by the mass flow rate of the air is equal to the specific volume of the dry air, which is equal to the specific volume of the mixture. And that's equations 1118 through 1120, respectively, working left to right. All right, and that concludes this this video. Tune in for the next one. We're going to talk about the American Society of Heating and Refrigeration Engineers and the